So good morning, everyone. Today's our topic is pericyclic reactions. So this one is our under unit first. So today we will cover this one unit first. That is pericyclic reaction. Now in this particular section we will study regarding the introduction. What is pericyclic reaction? The next one, classification, Hofmann-Woodward rule, electrocyclic reaction, sematotropic reaction, and cycloaddition reactions. Now first come to the point that what is pericyclic reactions. Okay, so now what is pericyclic reaction? Pericyclic reactions means, as the name indicates, these one are bond breaking and bond formation. Okay, pericyclic reaction means those reaction which in that reactions bond will be broken down and new bond will be formed in the cyclic transition state. Okay, new bond will be formed in that cyclic transition state. The next one, there is no intermediate compound of the charges. In this particular pericyclic reaction, you will not see any type of intermediate compound, either in the form of carbocation, carboanion, or any positive and negative charge components. Next, in these reactions, here the intermediate compound will be your cyclic transition state. It means the point at which maximum energy will be activated, or we can say that particular compound will be called as a activation, and in that compound having an activation energy. The next thing, in that particular cyclic transition state, new bond will be formed. Now these reactions are a stereo-specific reaction. Already I told you in the last class that what is the difference between stereo-selective and the stereo-specific reaction. The next thing, these reaction is a result of reorganizing the electron in the reactant. This thing you have to remember the main lines. Pericyclic reaction means where the electron will be reorganized in that particular reactant. Okay, these reactions, in these particularly pericyclic reaction, there will not be any type of catalyst or any type of catalyst and any type of reagent, etc. Here in these reactions are carried out either in the presence of, these reactions are carried out in two main conditions. First one is a photochemical condition, next one is a thermal condition. Okay, thermal condition means this reaction takes place at the absorption, without absorption of light, and the photochemical reaction takes place when the reactant absorbs the light. So these thing you have to remember, that these reaction are stereospecific, and there the electron will be reorganized in the reactant, and these reaction there will not be any type of intermediate compound, and these reactions are carried out either as a type of photochemical or as a thermal condition. And this one is the definition. Now the next thing, we will see the next slide. The next slide, here you can see, as I told you, these particular reaction are carried out in the transition state. As you can see, mostly in all the reaction you will see like this. There will be one starting material, there will be in the next one, and from the starting material and to the last one product, you will see different type of intermediate compound, right? Intermediate compound, there will be maybe there will be for formation of your carbocation, carbanion, like that. But here in the form of your this particular reaction, that one is electrocyclic, all the type of pericyclic reaction, you will see a something transition state. Transition state means there will be only one molecule where the bond will be broken down and new bond will be formed. So this one will be your particularly pericyclic reaction. Now we will start our main topic. Now the classification of pericyclic reaction. Classification of pericyclic reaction, these reactions are of three types: cycloaddition reactions, electrocyclic reactions, and the next one, sigmatotropic rearrangement. Okay, now firstly you have to understand these three things by their definition. Also, only you have to learn the main concept. If you have learned main concept, then surely you can write down all the definition also, and you can write down the reactions also. So they are three types: cycloaddition, electrocyclic, and sigmatotropic reaction. These are the example you will see here, but we will see in the next slide one by one. Now these are my notes. I didn't find a good concept in your favorite Google. So I just write down, this one is my notes. So hopefully you understand my writing. So now first reaction is electrocyclic reaction. Now what is electrocyclic reaction? Firstly, before starting, you should know the 2 points. What is intramolecular reaction and what is intermolecular reaction? And I have taught in the class also. Intramolecular reaction means within the structure, right? Intramolecular means within the structure, and intermolecular reaction means between the structure. Okay, so that one is intramolecular means within the molecule. As you can see, this one is particularly your one compound. In that particular compound, as I told you in the pericyclic reaction, electron will be rearranged. So now in this pericyclic reaction, intramolecular means within the molecule, electron will be rearranged. Okay, it can undergo a thermal or photochemical reaction. I had told you, in all these reactions, in the pericyclic reaction, there will not be any type of catalyst or any type of reagent. There will be only a condition, that one is thermal and photochemical reaction. Now what, just see here with more focus. This one is one compound is there. As you can see, how many carbon atom is there? 1 2 3 4 1 2 3 4 5 and 6 carbon atoms. Now there are 3 pi bond is there. Only you have to focus here, pi bond. There are 3 pi bond is there. Now electron will be rearranged. Now what will be happen? This electron will shift to this side, this electron will shift to this side, and this electron will shift to this side. This arrow represents a shifting of electron, or we can say a rearrangement of electron. And as I had told you in the pericyclic reaction, old bond will be broken down and new bond will be formed. Similarly, now you can see when this bond will shift to this side, it will become a like this. Okay, this bond will be shift to this side. So now it will be a single bond, and now this bond, it will be a double bond. You can see here. Now this bond will remain same. Now this bond will be broken down. It will make a new sigma bond like this. Here you can see this. Okay, this bond, it will make a new sigma bond like this. So here you can see, this one is a ring closure, this one is a ring open structure, while this one is a ring closure structure. There are a 3 pi bond, 1 2 and 3 pi bond. Here you will get only 2 pi bond, 1 and 2. So here is a, we can observe that there is a loss of 1 pi bond. As you can see, there is 3 pi bond, there is 2 pi bond. It means how much pi bond has been lost? Only 1 pi bond has been lost, while one new sigma bond is formed. So this thing you have to remember in the electrocyclic reaction. Now the now and here the bond will be shift in one direction only. Either they can shift to this side or they can shift to this side, either clockwise or anti-clockwise. So all the bond will be shift into one direction only. Now just see in another example, this one is a ring closure structure. Now this ring closure, it will be converted into a ring open. This one was ring open, it was converted into ring closure. Now this one is a ring closure, it will be converted into a ring open. Now you will see, again the old bond will be broken down and new bond will be formed. Now this bond will shift to this side. Here will be a new bond. Now this particular sigma bond, it will shift to this side, and you will see a new bond formation like this. So these all reactions are induced by light or heat, and these both reactions are reversible reaction. So this one under the topic your electrocyclic reactions. So we have observed that in the electrocyclic reactions, the loss of pi bond happened. Okay, and new sigma bond is formed. Now come to the next slide. Next reaction is our cycloaddition reaction. I think most of you well know about the cycloaddition reaction. What are cycloaddition reactions? Cycloaddition reaction means, as the name, this one is cyclo, it means two particular conjugated system will combine with each other as an addition reaction, and they will make a ring structure or cyclic ring structure. This one is called as cycloaddition reactions. Okay, here the particular, this one is starting material, as this one is our butadiene structure. So this one is butadiene. So this particular reactant we will give the name as a diene, while this one, that one is our CH2 double bond CH2, we will give the name as a dienophile. And the product which will be formed, that product is named as a adduct product. Okay, this one is the termed as a adduct in the case of cycloaddition reactions. Okay, so this one was, again, just see, this particular cycloaddition reaction consists of a addition of conjugated diene to second unsaturated molecule, okay, as a dienophile. Here this one is an unsaturated molecule, it will combine to another this one is a conjugated system, right? This one conjugated system is called as our diene, and while this one unsaturated compound is called as a dienophile, and resulting the formation of cyclic compound is called as a adduct product. And this addition reaction in which the ring system are formed without the elimination of any product, is called as cycloaddition reactions. Now you can see, again, this bond will shift to this side, this bond will shift to this side. So because if here we have to make a cyclic compound, when this bond will shift to this side, it will make a here the new bond will be formed. Now this bond, it will shift to this side, it will make a bond like this, and this bond will remain same, and now this bond will shift to this side, it will make a this one particularly a cyclic ring. Now we have to count, and here how many carbon at here how many pi bond is there, because this one is intermolecular reaction. Intra means within the molecule, inter means between molecules. It means the two molecules are combined with each other to make our final compound. That one is our adduct. So here in this intermolecular reaction, we can observe that there are 2 pi bond is here and 1 pi bond is there. It means 3 pi bond are joined with each other to make, and these 3 pi bond are converted into a 1 pi bond. It means there are a loss of delta pi, means the delta pi indicates there is a loss of 2 pi electrons. Okay, here is a loss of 2 pi electron, while 2 sigma bond is gained. Here you can see, because this one will make a 1 sigma bond, and this one will make a 1 sigma bond, right? So there will be formation of 2 sigma bond and 2 pi bond will be lost. Now we will see the next example. This one is the 2 particular molecules. Now this bond will shift to this side, this bond will shift to this side. Now it will make a, again, this one is a ring structure, and here 2 pi bond is lost. As you can see, there are 2 pi bonds, so 2 pi bond will be lost, and here 2 sigma bond is gained. So this one is the concept under our cycloaddition reactions. So these reaction is carried out either by a heating components alone or in an inert solvent. Now again, this one is the similar thing. That one is a Diels-Alder reaction. This cycloaddition reactions, this one is a cycloaddition reactions. This is the Diels-Alder reaction is the type of cycloaddition reactions. This is remains same, which I had told you in the last slide. Now the next reaction is our sigmatotropic rearrangement reaction. Now what is sigmatotropic rearrangement reaction? Sigmatotropic rearrangement means this one is the, now just read one line. This one is the reorganization of electron, as I told you, without the loss of sigma and pi electron. We have observed in the case of electrocyclic reaction and as well as electrocyclic reaction and cycloaddition reaction. In the both reactions, electron was lost also and the electron was gained also. But in the sigmatotropic reaction, without the loss of sigma and pi electron, the electron will be reorganized. Here this reaction is also intramolecular reaction. The electrocyclic reactions and electrocyclic reaction was also intra, sigmato was also intra, while cycloaddition reactions was intermolecular reactions. So this one is the main difference, so that you can learn, and on that basis you can draw the structure also. Now in this sigmatotropic reaction, just see, this one is our 1 molecule is there. In this particular 1 molecule, we will see, just forget about this one substituent. This one is our substituent, so you just forget about this one methyl group. Now only we have to just old bond we have to just broken down, a new bond we have to make. Now here this bond will shift to this side, this bond will shift to this side, this bond will shift to this side. So you can see, when this bond will shift to this side, it will make a bond like this. This bond will shift to this side, so here bond will be like this. Now there will be no bond, and this, so here will be new sigma bond is there, right? So there is a new sigma bond. Here there was a 2 pi bond in the starting material, there was 2 pi bond. Here you can see there is also 2 pi bond. Here is how many sigma electron? 1, 2, 3, 4, 5. Here is also 1, 2, 3, 4, 5. There is also 5 sigma bond. It means there is no loss of pi bond is there. And sigmatotropic, as the name indicate, it means there will be a sigma electron will be either there will be a new formation will be there. So now you can see here this there is a formation of new formation of a sigma bond without the loss of sigma or pi electron. Now come to the next topic. Yeah, so this one I have not make a table, but I think hopefully you can understand. In the electrocyclic reaction, there will be in the electrocyclic reactions, one new sigma bond will be add and one pi bond will be lost. In the cycloaddition reaction, 2 sigma bond will be formed and 2 pi bond will be lost. But in the sigmatotropic reaction, neither sigma bond nor pi bond will be lost. Okay, now the next topic is our Woodward-Hofmann rule. Now what is Woodward-Hofmann rule? The Woodward-Hofmann rule, which was given by Woodward and Hofmann. But what is the rule? According to him, he has given he described about the series of the rule which predict whether a pericyclic reaction process occurs under thermal or photochemical condition. Okay, we have to identify that these reactions are carried out either in a photochemical or in a thermal condition. But the main point is these all the reactions are based on orbital symmetry only. Sorry, these reactions are based on orbital symmetry only. Firstly, we should learn what is molecular orbital. As I taught you in the first year yours, that what is orbital symmetry. Sorry, what is the molecular orbital? So what is molecular orbital? Molecular orbital which describe the behavior of electron in the molecule. Okay, molecular orbital means which describes the behavior of electron in the molecule only. Now we have only here you have to read this thing, but now I know very well that you will not understand after reading this thing. What is this one? Positive lobe and negative lobe. Now listen me careful, then only you will get all these things. There all the carbon atoms or all that particular compound, we have to, in all the particular reaction, we have to identify we will draw the structure of the lobes of. Okay, we have to draw the structure of lobe of orbital. One thing you have to learn it from here, that the lobe which will be shaded, that will be a positive. The lobe which will be unshaded, that will be negative lobe. Now come to this side. Firstly, we should know very well that molecular orbital means which describe the behavior of electron in the molecule. The next thing, these molecular orbitals are two types, HOMO and LUMO. These molecular orbitals are two types, HOMO and LUMO. Now what is HOMO? What is LUMO? Firstly, we have to learn this thing. HOMO means the full form of HOMO. That one is a highest occupied molecular orbital. You can write it. HOMO full form, highest occupied molecular orbital. While LUMO full form is lowest unoccupied molecular orbital. Okay, lowest unoccupied molecular orbital. Okay, now we have to draw the structure of HOMO and LUMO of particular compound. So how will we draw the structure? Now just see here. Suppose that you have one compound. This one is one compound. How many carbon atoms is there? 4. So the name of this particular compound is butadiene. Okay, there are 2 ene group is there and 4 particular carbon atoms. So this one is our butadiene. This, what is this one? This one is our 1, 2, 3, 4, 5, 6. This one is our hexatriene because there are 3 double bond. And this one is octatetraene because there are 8 carbon atom and tetra means 4 double bond is there. So this one is octatetraene. And now we have not to consider about their name. We have to focus here. Firstly, we have to observe there are firstly we have to see the lobe. We have to count the first lobe and last lobe. This x indicate there are 2 lobes is there, first lobe and this one is last lobe. Now you have to draw the structure like this. This one is the structure of lobe. Okay, lobe, first lobe, last lobe, first lobe, last lobe. Everywhere the structure remains same, right? This one is the first lobe, this one is the last lobe, and both lobes are connected with one particular bond. So both lobes are connected with a bond. One side I have written here HOMO, one side I have written here LUMO. But now we have not drawn the structure of HOMO and LUMO. This one is the only indication. How will you draw this? This one is the lobe of molecular orbital. Now how will we draw the structure? Now how will we draw the structure of HOMO and LUMO? Now we have to learn the first thing. Here I have not shown here the one particular trick. If you want to write, then you can write, please write down, or otherwise I will tell you tomorrow. The one thing you can write down, that even LUMO symmetry, this thing you have to learn it. Even LUMO symmetry, it means what does it mean? It means firstly you have to see here how many, even means there are how many pi bond is there. Now just see here how many pi bond is there in first compound. There are only 2 pi bond is there, right? There are only 2 pi bond here, 1 and 2. 2 pi bond, it means there are a even number of pi bond. If there are even number of pi bond, it means now the LUMO will be found in symmetry form. Symmetry form means here you can see the both lobes, just means it means face to face. Both lobes are a shaded form. Okay, and it means if both lobes are found as a shaded form in the LUMO, it means in the HOMO it will be a asymmetry. As you can see, this one is asymmetry, but while this one is a symmetry form. Now just see the next one. In the next example, please listen carefully. In the next example, here how many pi bond is there? 1, 2 and 3. 3 pi bond is there. 3 pi bond means this one is the this pi bond is a odd in form, right? These are odd number. 3 pi bond, in the whenever you will find a odd number, it means their HOMO will be symmetry. If odd means HOMO will be symmetry, it means HOMO, just see the structure here, HOMO will be symmetry. So you have to just set this particular symmetry form. HOMO will be symmetry. If HOMO will be symmetry, it means LUMO will be asymmetry. Now come to next one. Here is also how many pi bond is there? 4 pi bond is there. 4 pi bond is there. It means this one is an even number. Even number means even LUMO symmetry. It means here the LUMO will be symmetry, while this one HOMO will be asymmetry. So okay, this thing you have to firstly you have to see in any molecule how many pi bond is there. Based upon the pi bond, you should know the firstly trick that even LUMO symmetry and odd HOMO symmetry. If that one is a odd number, it means HOMO will be symmetry. If that one is an even number, it means LUMO will be symmetry. If one is symmetry, it means another will be asymmetry. Okay, now we will find the another trick. Another trick to learn about the Woodward-Hoffmann rule. Now we have to learn the trick. This one is the shortcut method. This one is the shortcut method to learn about Woodward-Hoffmann rule. Now what is this one? Woodward-Hoffmann rule? Only you have to listen it. If you will listen, then surely you can attempt all this thing and you will get to know. Woodward-Hoffmann rule, before starting we have to learn this one. ETCA, OPCA. ETCA, OPCA, it means either I have just learned it like this. Etka, Opka. Okay, Etka, Opka. So Etka, Opka means E means event, T means thermal condition, Con means con rotation, Antara facial. Okay, I will describe each term. Even, thir, con, antara. Even number of pi bond. Thir means thermal condition, con rotation, and antara facial. Opaka means odd number of pi bond. Then photochemical condition. Next one is con rotation and antara condition. Antara facial. If you have learned this one black sided, this one lines, then surely you will attempt. If this particular things or this particular condition is not suitable for your particular reaction, then what will you do? Even photo, if this is not in thermal condition, it means it will be a photo. If this one is a photochemical reaction, it means there will be a disrotation. This one was conrotation, that one will be a disrotation, and it will be a suprafacial. Now, if odd should be always a photochemical condition, but if it is not in a photo, it means it will be a thermal condition. If it is in a thermal condition, it means there the rotation will be a disrotation, and the rule will be and there will be a suprafacial condition. Now we will see. Now come to this one. Now we have to focus here. What is, now we know very well, even and odd means this one is an odd number and even number of pi bond, and photo means photochemical condition and thermal chemical condition. Now we have to see what is conrotation, what is disrotation. So what is con and rotation and disrotation? Here we have to see. Let me say it is a lobe, and this lobe is found in a asymmetry form. Okay, let me say this is a lobe, and this lobe is found in a asymmetry condition, as you can observe from here. Here you can see this one is symmetry in condition, because in the front of both lobes are both lobes are shaded in form. It means both lobes are a symmetry form. Here both lobes are a asymmetry condition. When they are asymmetry condition and we have to rotate particular lobe, then what will be happen? This particular lobe, it will rotate to this side and it will rotate to this side to make a new bond. Okay, to make a new bond. Now what will be happen here? This one is, see, either they can rotate a clockwise or they can rotate a anti-clockwise. Clockwise and anti-clockwise. This one is a clockwise, this one is the both are in a clockwise condition, right? So either they can rotate a clockwise direction or anti-clockwise direction. When it will rotate to this side, so it will become like this, and when it will rotate to this side, it will become a like this. So now they will make a bond. There will be a new sigma bond is forming. Here we can see there is a new sigma bond is forming. It means here lobes are matching. Lobes are matching. New sigma bond is forming, right? So when they are when the lobes are matching and they are forming a new sigma bond, and when the both lobes are rotated in a unique direction, it means when the both lobes are rotated either in clockwise or in an anti-clockwise direction, so that rotation is called as conrotation. As I told you here, that rotation is called as conrotation. Now what is disrotation? Let me say this orbital, it is of a symmetry lobes, and when these lobes are rotating, so these lobes will be rotate like this. One lobe will rotate in a clockwise direction and one lobe will rotate in a anti-clockwise direction. So because they are or we can say, or we can understand, yeah, first is see, when it will rotate to this side, so this one will be like this, it will be like this. So both are matching, they are making a new sigma bond. But here we have to focus that here this rotation are found in a opposite